Yeah, I just highlighted like the two most variable ones and everything.
All right, everyone, welcome to the seminar series hosted by the New Zealand Mass Society. It is my great pleasure to introduce our speaker. I'm Professor Beyer, University of Otago, and I'm going to introduce Florian Beyer, who joined our department in 2009 and really doesn't need much of an introduction to New Zealand Mass Society, but in case you're not quite aware, he's a much respected member of our department since 2009. He got early career award from the New Zealand Mass Society in 2013, has been on the council from 2014 to 2020. He also organized a colloquium in 2018, and today he's going to talk to us about nonlinear stability, mathematical cosmology. Take it away, Florian.
Well, thank you very much, Boris, for your kind words, and thanks very much to the New Zealand Mass Society for giving me the opportunity to talk here about some of my recent work, most of which is done in collaboration with Todd Olinek from Monash. So, well, I'm talking about some nonlinear stability problems in mathematical cosmology. I will, of course, explain what I mean by that, but in a nutshell, mathematical cosmology is basically mathematical problems motivated or derived from cosmology. And I hope I can convince you today that there's really a very rich kind of mathematics that you can derive from cosmology, given that cosmology is essentially geometry, and geometry is essentially, I mean, some people might not agree with me, but geometry is essentially nonlinear partial differential equation. So there's a very natural relationship. And I want to convince you today, hopefully, that mathematical cosmology is particularly interesting to mathematicians, maybe even more so than to physicists in some respects. So I'm definitely not a full, deep expert on physical cosmology, but let me very quickly go into some background motivation for cosmology. So where this whole thing coming from? So in cosmology, we want to describe the history of our universe, and we have a very successful model that is the so-called Lambda cold dark matter model, CDM model here, sometimes also called concordance model or standard model, which is amazingly amazingly successful because it can explain all kinds of different observations in a very consistent way. So it's really surprisingly and astonishingly consistent. And it is derived from using Albert Einstein's general relativity plus a few other bits, and I will explain a little bit of that. And the idea about the history of our universe that we get from this model is very, very simplified as follows, that our universe started about 13 to 14 billion years ago in something that people call a Big Bang. We don't know exactly what the Big Bang was and what made it happen. But in any case, ever since this Big Bang, our universe has been expanding. And it has been expanding, so becoming larger with different speeds, different rates at different times. So in the very early universe, there was apparently a phase of very rapid expansion that we call inflation. And then once this was over, there was a phase of sort of decelerated expansion, mostly driven by the attractive gravitational force of normal matter. But then in the more recent history of our universe, so-called dark energy has been dominating the dynamics of the universe. People argue a lot what dark energy is, but the main effect of dark energy is that it accelerates the expansion. It pushes our universe apart. And well, this model has been very successful. I've already said that. But from a certain theoretical point of view, it is probably not fully satisfying. It is, in particular, it does not use the full nonlinear geometric theory. It is based on certain approximations. So for example, one of the assumptions is that on very, very large scales of our universe, which would be scales beyond 100 million light years or so, the description of our universe becomes very simple. We can describe it by very, very simple solutions of the simple model, very simple models, and I will give you the model in a moment that we are talking about here. And then everything that happens on smaller scales is essentially described by linearized perturbations. I mean, there are also more modern efforts where people also trying to take into account some non-linearities, but at least to my knowledge, and at least not in the rigorous setting, there has not really been any sort of attempt to really take into account the full nonlinear nature of the theory that we're going to explain. So in particular, the nonlinear theory, or it is a question whether the full nonlinear theory really allows us to separate the dynamics of the larger scales from the dynamics of the smaller scales, as we sort of do in this model here, or whether there's really a nonlinear relationship. And in particular, this might be true in the very, very early universe that I want to mostly talk about today, when the universe was very small. And a very natural question then arises about the stability of that simple model here. So the question is, okay, observations suggest that our universe is, at least at the present time, nicely explained by this lambda cold dark matter model, by the very successful model, but it is not exactly, does not exactly agree with that model. So there will be small perturbations, small errors on top of that. And then the question that I would like to address here is, how do these small nonlinear perturbations evolve over time, in particular globally in time towards the beginning and also the end, in quotation marks, of our universe. So this is really a question about the full nonlinear nature of the theory, if you wish. And I, of course, will make that more precise a little bit later. And I guess I will re-emphasize that again and again, but the equations that we're addressing in cosmology, so the so-called Einstein's equations, are tremendously complicated set of partial differential equations. And really, a question like the nonlinear stability of the full theory is extremely hard, because you cannot just sort of I don't know, estimate or approximate certain terms. You really have to take every term in the equation and see what it does dynamically. And until, I don't know, recently, maybe 10 years ago, the question of nonlinear stability of this kind of cosmological models here would have been considered as basically undoable. And only the last sort of maybe 10 years, the last few years, we have made some mathematical progress. So in particular, progress on the theory of nonlinear PDEs. So in a very simplified picture, as I said, cosmology is based on Einstein's theory of general relativity, and in particular on Einstein's equations. So let me give you a very, very simple picture. So the universe, we in this theory, we understand as a Lorentzian manifold that with a natural, at least mathematical natural assumption of global hyperbolicity allows us to think of as a Cartesian product of the real line that sort of contains time or describes time, and a spatial manifold here that describes space, obviously. And so this is a very rough picture of our universe, where sort of time goes up, and each cross section here, so each copy of that manifold sigma here is the spatial universe at one moment of time. Okay, so that's the idea. So this whole thing is called, the whole Lorentzian manifold M is called space-time. And the main subject of Einstein's theory is then the Lorentzian metric that lives on this space-time, that describes the geometry of the Lorentzian metric, and the curvature is interpreted as gravity in Einstein's theory. So what is this Lorentzian metric? So a metric in differential geometry is essentially a scalar product that you know from, I don't know, Euclidean geometry or so. So a way to measure length of vectors or angles of vectors. So really that allows us to do basic geometry. But in Lorentzian geometry, this metric here is not positive definite. It is, well, it's of Lorentzian signature. What this means is that this metric here can distinguish in a geometrical way time and space. And when you induce that metric on any of these constant time hypersurfaces here, then it becomes positive definite. So the geometry that is induced on each of these hypersurfaces sigma here, so these moments of time of our universe, this is standard Riemannian geometry, but the Lorentzian manifold, a Lorentzian metric also takes into account how these Riemannian geometries here are embedded in the space-time. So how they look, how they appear in the space-time. So this metric here, this is the main geometric subject of Einstein's theory. This is what describes gravity. And the Einstein's equations are now a very simple looking equation that takes this following form. Again, very short in a nutshell. So the Einstein's equations are a condition for this Lorentzian metric. And the idea is, roughly speaking, that gravity is generated by masses somehow sitting in our universe. And gravity is essentially curvature. So somehow curvature should be, and that's what the Einstein's equations say, curvature should, roughly speaking, be proportional to the amount of matter in our universe. A little bit more precisely, it's not the full curvature tensor, namely the so-called Riemann curvature tensor that we control in the Einstein's equation, but a certain trace of the full Riemann curvature tensor, namely the so-called Einstein tensor. And Einstein's equations say that this trace of the Riemann curvature tensor, so the Einstein tensor, should be proportional. So this is just a constant here that we can assume to be 1 by choice of units, as mathematicians do. That should be proportional to this quantity T here that describes the amount of matter. It's the so-called energy momentum tensor of the matter in our universe. So on this level, Einstein's equation look extremely simple. It's a linear relationship between curvature and the amount of matter. The problem becomes difficult once you want to understand this equation as a differential equation for the metric G. So somehow you want to understand this Einstein tensor here as a differential operator acting on G, and you essentially want to invert this differential operator to determine a metric G from this equation. This is where things become really hard, and this is where you really see what kind of beast the Einstein's equation are. And the first problem that you encounter is, by the very fact that this is a geometric equation, that this equation must be degenerate as a partial differential equation. And the reason, or the source of this degeneracy, is simply the diffeomorphism invariance of geometry. So this means that a metric here can only be uniquely determined by a condition like that up to diffeomorphism, so up to coordinate transformations. So these equations have this geometric property and we have to live with that. And then for a long time, it was a big unsolved problem. How can we actually determine solutions from this degenerate equation? And it was only up to the 1950s that Yvonne Choucré-Bouhar really laid the foundation for our field. She found a way, and I don't have time to explain how exactly, to break the diffeomorphism invariance in this equation, and thereby turn the Einstein's equation into a non-degenerate set of partial differential equations with in particular have a well-posed initial value problem. And the initial value problem, as I will explain, is really the foundation for everything that we're doing here. So more precisely, the Einstein's equations become a system of wave equation, roughly speaking, for the metric G. So the metric G is the unknown that we would like to determine. So those of you who are not doing partial differential equation, this is here essentially this is the D'Alembert operator, which is essentially second time derivative minus second space derivative, but it's a nonlinear version of that. And in fact, it's nonlinear depending on the unknown metric itself. So this operator itself is already quite nonlinear, but it is good enough, or we understand it good enough to know that this operator always allows a well-posed initial value problem, which I explain in a second. And the right-hand side of the equation that I just symbolically write out here with this map G that depends on the metric, derivatives of the metric and unknowns, this is a horrible mess of nonlinear terms. And if you would write everything out in detail, in all glory, then it would fill a couple of pages. So this is a very complicated nonlinear operator, but it's only an operator in lower order terms. So what do I now mean by the initial value problem in the context of cosmology? So for the initial value problem, in the context of cosmology, we assume that we somehow pick an initial time. And by initial time, I don't mean the initial time of our universe, so the Big Bang time. I rather mean something like, say, the present time. It's the time when we know by measurements, say, the state of our universe. Okay? So this is the time where we just freely prescribe data for our initial value problem, initial data for our initial value problem. It's just an arbitrary time in the history of our universe or of a cosmological model where we believe to know the state of the universe at that time, meaning the metric and its first time derivative, essentially. So these are the initial data that we are allowed to prescribe on one of these hypersurfaces here that we correspond to our initial time. And these initial data are not allowed to be completely free. The Einstein's equation will imply certain constrained equations, which are mostly of elliptic nature, so like Laplace's equation. I'm not going to talk about those very much. The main point is that the evolution equations, given these initial data here, will then determine a unique solution at least in a time neighborhood of my initial hypersurface. So determine at least a piece of the history of our universe in a neighborhood of what I selected to be my initial time. Okay. So this is the initial value problem of the Einstein's equation. So this is essentially what we want to solve. Oh, and I forgot to say, in cosmology, of course, we're also interested in quantities that describe matter. So we would need to couple these evolution equations here, so this system of nonlinear wave equations here, with the equations for the matter, and these system of equations would be coupled to lower order terms here. And I will be a bit more specific later on. Okay, and for this cosmological nonlinear stability problem, there's now one particular very simple solution of the Einstein's equation of interest, and this is the so-called flat Fridman Lemaitre Robertson Walker solution. Sometimes I just say Fridman Robertson Walker solution, so sorry to Lemaitre, sometimes I forget mentioning you. And this is just a very simple cosmological model, but the point of this cosmological model is that it does, to some extent, correctly model the history of our universe. In particular, it implies that in the distant past, we had something like a Big Bang. Okay? And for this solution of the Einstein's equation, the Lorentzian metric takes this form here. I don't really want to explain all the details here, but what this means is that the induce geometry on each of these hypersurfaces here. So each moment of time of the universe, like these spatial universes, is essentially just the Euclidean metric. So just standard Euclidean geometry multiplied with a scale factor that just gives us the size, if you wish, of the spatial universe. And this size function, which we call the cosmic scale factor, is allowed to depend on time. And in particular, when we follow this solution backwards in time, so towards, well, backwards in time, then this scale factor function will shrink, will become smaller. And typically, depending on the matter model that we're looking at, it will shrink like a power of t. So at, say, t equals 0, depending on how you choose your coordinates, at t equals 0, the scale factor function here will go to 0, and this whole geometry here will become singular. And in fact, you can show that depending on what this p really is here, you can show that the curvature tensor blows up, and also matter becomes infinitely dense at this time when the scale factor goes to 0. So this is the sort of base model of the history of our universe. And in particular, it has this feature that it has a big bang singularity at some finite time in the past. And now the nonlinear stability problem in cosmology is now the question how stable this particular solution is. Okay, so, and what do I mean by stable? I mean now, so I mean this now from the point of view of the initial value problem. So I'm not going to approximate the equations in any way. I'm really going to take the whole full set of equations into account. So the idea is the following, that so at some initial time, say the present time or whatever, some arbitrary initial time, which I choose as my initial hypersurface, I want to study what happens if I choose as my initial data, not the exact Fridman Robertson Walker data, which would give me that simple model that I just explained, but it would give me some perturbed solution. So I choose some initial data close to the initial data of the Fridman Robertson Walker solution. And by what I mean by closeness here, well, that's something I will have to be determined when I do the analysis later on. So for the moment, I can only pose this question sort of on this intuitive level. Later on, I will get to tell you exactly what I mean by closeness here. So if I choose data close to Fridman Robertson Walker data, and then look at the solution of the initial value problem of the full Einstein's equations and the full matter equations coupled, corresponding to this initial data, then I want to understand if this solution globally in time, in particular backwards in time, that's what I'm interested in here today, will stay close to the Fridman Robertson Walker solution. So will it behave dynamically globally in time, similar to the Fridman Robertson Walker solution, and in particular whether all these perturbed solutions will also have a big bang like the Fridman Robertson Walker solution. Okay, and if we can answer this question, yes, then it would at least to some extent confirm the lambda cold dark matter model, because at least it says that it's a good approximation at least to use the Fridman Robertson Walker solution as our base solution. So this is the main question. And at this point, it's usually physicists who say, oh, that's not very interesting. In particular, when you sort of questions about sort of the asymptotics at the Big Bang singularity are not really relevant because we will probably not be able to observe those anyway. And we also, honestly speaking, don't really know the laws of nature. So whether the Einstein's equations are really a good system of equations to describe that epoch, well, that is probably true, or nobody knows what is true or not in this early phase of the universe. But I would still argue that this is interesting for physics fundamentally. But in particular, for this talk today, I want to argue that these kind of questions are interesting for mathematicians. So and one way I want to do this is just to show you the history of similar nonlinear stability problems that appear in that are derived from cosmology, or more general from Einstein's theory. And the first kind of nonlinear stability result was about the so-called de Sitter space by Helmut Friedrich in 1986. I'm not going to talk about that very much because I think at that time when it was published, it was not really understood how relevant that result was. the first time when mathematicians really became interested in this kind of nonlinear stability problems derived from Einstein's equation is when Christodoulou and Kleinerman derived or proved the nonlinear stability of Minkowski space. And when you think about this, this is in some sense a ridiculously simple setting. Minkowski space is the trivial solution of the Einstein's equation. It's completely empty, the zero curvature, so it's no gravity and no matter whatsoever. So it's really the simplest solution that you can look at. But it was not known when you now introduce small perturbations in this sense of an initial value problem to that kind of simple solution. What happens to those dynamically? In particular, what happens to those small perturbations as they dynamically reach infinity? And you want to derive precise decay estimates and all these things at all different kinds of infinities that you can have in such a space-time. So this result by Christodoulou and Kleinerman is a couple of 100 pages and was published in Princeton University Press here in 1994. And then it was considered as a huge step forward also that there was a result by Lindblad and Rodniansky in 2010, which came up with a shortened proof of only about 100 pages of nonlinear stability of Minkowski space, which was then published in Annals of Mathematics. So I think, I mean, I just mentioned that mainly to show those skeptical mathematicians among you that physical problems derived from cosmology are definitely of interest to mathematicians as well. And then a few years after this, 2010 here, in 2014, I think this result was announced, there was finally a nonlinear, the first nonlinear stability result of that cosmological solution that I've just shown you, the Fridman Robertson Walker solution here by Rodniansky and Speck. And myself and my collaborator have recently submitted a new version of that proof, in particular, a shorter version of that proof. So what the reason why that result by Rodniansky and Speck in 2014 was considered as such a breakthrough was that it was the first time that it was possible to show a nonlinear stability result for an equation as complicated as the Einstein's equation around a singular solution. All these solutions before, like Minkowski space and de Sitter space, are all completely regular, in some sense boring solution. But the Fridman Robertson Walker solution has a singularity. And understanding the stability of the solution near a singularity of a very complicated nonlinear equation is very hard. And so this was considered as a big breakthrough. So they published this result in 2 papers, combined a number of pages of 250 pages. One of them was published again in Annals of Mathematica and the other one in Selecta Mathematica. And well, one of the contributions, but that's not all, I talk about later, of our new result is that it's only 50 pages. And then, so this is the result I mainly want to talk about today. Just for completeness, I want to tell you that also recently was announced a breakthrough in the improving a nonlinear stability result for black hole spacetimes. Again, I expect that this will be published in a journal like Annals of Mathematics or so. But the point again here, I would say, is that these kind of proving a nonlinear stability result rigorously is probably more of interest to mathematicians than to physicists, because physicists will probably claim that they already knew that a black hole was stable for many years, right? From there, physicists know everything already. Sorry to my physics friend out of there. I'm not trying to make fun of you. In any case, today I want to talk about this kind of result here. And before I give you the precise version of the result, I just want to show you what you can expect and what you cannot expect. And the problem is always when you're working with nonlinear differential equations in regimes where you don't have much intuition, like near the Big Bang or so. I mean, that's very far from our everyday experience, what is happening there. We don't really know what to expect, and we don't really know what we can prove. Right? So over many decades, what people did was therefore to gather experience by doing heuristics, by doing numerics, very useful, or just by looking at special cases. So here I just want to quickly talk about a very special case namely the so-called spatially homogeneous case, which is the same, essentially the same nonlinear stability problem, but for perturbations up here, which are in some sense constant in space. Okay, and what that means is that the partial differential equations of Einstein's equation just reduce to a system of ordinary differential equations, which makes it much easier to handle. And in fact, you can introduce quantities, so variables, that turn this equation into an autonomous dynamical system. So you can really use dynamical system theory to analyze this kind of problem here. And I think if I remember that right, the dynamical system is something like 8-dimensional or so. And here I'm just showing in this sketch here, I'm just showing you a 2-dimensional hypersurface in there spanned by 2 variables, sigma plus and sigma minus, which I'm not even going to define now. But what these variables measure is the anisotropies of these solutions. So I haven't really said that, but the Fridman Robertson Walker solution is an isotropic solution, which means that from any point in space-time, when you look out, there's no preferred direction in the sky. All directions in the sky look the same, while these solutions that you can generate here have in general anisotropies. But the Fridman Robertson Walker solution has no anisotropies, so it's sitting somewhere in the origin of that 2-dimensional hypersurface. And in fact, the Fridman Robertson Walker solution is a fixed point of that dynamical system. So all the singular dynamics that I talked about before has been scaled out by the choice of variables. So here we have the Fridman Robertson Walker solution, and there's another whole family of fixed points sitting on this circle here. Is called the Kastner solutions, which are also solutions of the Einstein's equations, but they're very anisotropic. And now, what is our nonlinear stability problem? So we try to now take the Fridman Robertson Walker solution at some initial time and just choose some data there that is not exactly Fridman Robertson Walker, but something close to it. So my picture here, my initial value would maybe be some point in the state space close to Fridman Robertson Walker. I mean, this is all very schematic here. And then what I want to do, I want to look at the dynamics of these initial data under this dynamical system, and in particular ask what kind of stability I can expect. And now what I see is that when I now follow the evolution backwards in time, so as I said here, towards the singularity, we are moving away from the Fridman Robertson Walker solution. So the Fridman Robertson Walker solution is past unstable. Okay. So that sounds really bad, right? In particular, in comparison to what I talked about before, that we want to prove a stability result of the Fridman Robertson Walker solution. But here we clearly see it's not stable. The solutions move away from Fridman Robertson Walker solution to the past. They move towards Fridman Robertson Walker in the future. But we're not interested in the future here. So, and I want to say it's even worse than that. Oops, going the wrong way. It's even worse than that, because it's not only that the solution moves away from Fridman Robertson Walker solution, but there's also a very, very complicated dynamics that happens after that with bounces on these Kastner circles, and in fact, an infinite sequence of bounces on this Kastner circle. So it's a never-ending sequence of bounces and these kind of orbits that we see there. So the solutions have no chance here to converge. In particular, it's absolutely hopeless to even think about proving stability of the Fridman Robertson Walker solution in this setting. And this complicated dynamics here was christened Mixmaster dynamics in the 1970s, because apparently there was a very popular kitchen mixer called Mixmaster, Sunbeam Mixmaster or something like that. So Charles Miesner called this dynamics Mixmaster dynamics after that kitchen mixer. So that looks completely hopeless. Okay, but one thing that I haven't talked about here is, I say up here, in vacuum. In fact, the same result I would get if I have matter in my universe, ordinary matter in my universe. So ordinary matter if I couple the Einstein equation to ordinary matter, I would essentially get the same dynamics. So now one of the tricks in cosmology, and probably I don't want to offend anyone, but the trick in cosmology is that whenever you have a problem, you design and impose a hypothetical new matter field whose dynamics somehow fixes the problem. And that kind of approach has been very successful also for the lambda code dark matter model, so the standard model, for example, to introduce something like inflation. And the simplest way to design a matter field that somehow fixes your problems is to use scalar fields. And I don't have time to tell you exactly what a scalar field is, but a scalar field is a function described on space-time, say a real function or so, that satisfies some sort of wave equation, and that is coupled to the Einstein equation in a particular way. So it acts like matter, but it is an extreme kind of matter because it has a very significant influence on the asymptotic dynamics in particular. That was realized for the first time heuristically by John Barrow, and he found that if we use scalar fields, we can essentially switch off that nasty Mixmaster dynamic that I talked about before, and he talked about a scalar field that can do it. He called that quiescence, coming from the word quiet and essence mixed together. And so how does that work in our picture here? So now if we introduce a scalar field as a matter field and look at the combined Einstein scalar field system, and I will say a little bit more about this later, then we have, and now for the moment, just specialize to the spatially homogeneous case again, so the spatially constant space again, and look at our dynamic system that we get. The Fridman Robertson Walker solution will still sits in the origin of this plane here. But now the vacuum Kastner circle, remember that was the circle where all these nasty bounces happened before, is now replaced by a smaller circle, and of the circle of fixed points of the dynamical system, again, which we call Kastner scalar field circle. And this, and when we now look at the dynamics, what we see is, so we again look at initial data close to Fridman Robertson Walker data and then evolve it backwards in time. Again, the solution will drift away from Fridman Robertson Walker, but now it will converge to a point on this Kastner scalar field circle. And since this Kastner scalar field circle and the radius of that circle is determined by the amount of scalar field, in quotation marks, that is present, we can assume for our nonlinear stability problem that we have an amount of scalar field available very close to the amount that corresponds to the Fridman Robertson Walker solution. So we can confine the dynamics to a very small circle around the Fridman Robertson Walker solution. And we know, at least in the spatially homogeneous case, that the dynamics will be confined to that circle whose size I can make as small as I like. So in that sense, we can expect a stability result for a Fridman Robertson Walker solution coupled to a scalar field, but that would be a kind of orbital stability and not asymptotic stability. So it would not be asymptotic stability would mean that the solution, the perturbed solution, would converge back to the Fridman Robertson Walker solution, which is not the case here, but at least the solution will stay close to the background solution, to the Fridman Robertson Walker solution. So we will get some sense of orbital stability, hopefully. But this is all just spatially homogeneous here. So the interesting thing, of course, is now what happens for arbitrary perturbation. And this is what Wozniacki and Speck in their breakthrough result from 2040 were able to analyze. So they were able to analyze exactly this question that we posed before, but not for the Einstein's equation, but for the Einstein's equation coupled to a scalar field. And so the stability of the Fridman Robertson Walker solution. So the question, what happens if I have initial data that is close to the Fridman Robertson Walker data? What happens to that dynamically, globally, and time towards the singularity? Does the solution stay close to the Fridman Robertson Walker globally in time, and what kind of asymptotics can we expect in the Big Bang? And they were able to prove, so this is my informal result here, is just say yes, and I will give you the precise version of this result a little bit later. So the answer to this question is yes, we can control the dynamics, and the dynamics will stay close to the Fridman Robertson Walker solution, and we can find a precise notion, precise equivalence of this notion of orbital stability that we have identified in the spatially homogeneous case. Yeah, exactly. So the informal result is that the answer to this question is yes, right? And this means that at least if we accept that in the very early universe, we had some funny scalar field around that that stops this Mixmaster dynamics from happening, that then we know that the Fridman Robertson Walker solution is nonlinearly stable globally in time. So before I give you the precise version of this theorem, let me just tell you one particular problem that you encounter when you prove that, and the different ways that Wozniacki and Speck and myself and my collaborator solved that problem. And that's the problem of that is sometimes called singularity synchronization. So what you can, I can explain that problem simply as follows. So remember that we want to solve this initial value problem, and suppose that we maybe just first time that we just solve the initial value problem with data that are exactly Fridman Robertson Walker data. So that means that the solution is constant in space. So, and it stays constant in space during the evolution. So this means that the singularity here is approached dynamically uniformly in space. So every point in space approaches the singularity with the same speed, if you wish. But now, when we now look at perturbed initial data, so initial data that is maybe a little bit larger over here, that is over here, or whatever, you can expect that this, unless you're careful, that in general, the singularity will be approached in a non-uniform way. So some parts in space might approach the singularity faster than others. And this is a consequence of the general diffeomorphism invariance of the theory. And the fact that coordinates, so particularly the time coordinates that control this time equals constant surfaces here, are determined during the evolution, and we have no a priori control where these hypersurfaces are because only once we have actually found the whole solution, so the whole space-time solution, so the whole cosmological model, only then we can determine where in this cosmological model our time equals constant surfaces are. So this is just a problem that we have never a priori control of what coordinates are, of what our coordinates mean, and coordinates can easily also break down during the evolution. So Wozniacki and Speck, I'm really running out of time here, so I need to be a little bit quick here. So what Wozniacki and Speck did in their 2014 result, they imposed a geometric condition on these time slices here, namely a constant mean curvature condition. And they essentially use the constant mean curvature of each of these slices as a time coordinate. And when they did the analysis, then they showed that in this time, with respect to this time foliation, the time slices approach the singularity uniformly in space. So the singularity is synchronized. And this is very nice. I mean, I'm not saying anything against this. The technical problem with this kind of approach is that the constant mean curvature condition is a global condition in space. In fact, the equations that you get is you get your system of nonlinear wave equation that we had before coupled to an elliptic equation. So an equation like the Laplace's equation, essentially, which introduces infinite speeds of propagation into the problem. So when you have a system of wave equation, then all the perturbations can only travel with finite speeds. That's one of the most fundamental properties of wave equations. But when these wave equations are coupled to something like an elliptic equation, then you also have components in there that travel basically with infinite speeds. And so in particular, this means that their result here, Wozniacki and Speck result, cannot be localized in space. It's really a global problem in space. So the result that they prove, therefore, only holds for that particular spatial manifold that they chose. And they, for simplicity, chose a torus as the spatial manifold. So they assume that our universe is a torus. which of course nobody knows whether this is true or not. So their result only holds if our universe is a torus. And it was then ever since a question whether one can somehow localize the result so that it makes sense without making any assumption about the global topology, about the spatial manifold. Okay. And this is something that we have achieved because we managed to synchronize the singularity in a different way that does not use these global in space conditions. Namely, what we can do, what we were able to do is to synchronize the singularity by choosing the scalar field as a time coordinate. So each of these surfaces here in our picture are surfaces of constant scalar field. And because the scalar field satisfies a wave equation, the whole system of equation written in those coordinates is a system of wave equation. So it has finite speeds of propagation. So our result, that in the first instance we also prove on a torus, can then be localized. So we were able to show that our result, when we just restrict ourselves, say, to an open subset of initial data in the initial hypersurface here, and that our result then holds on the domain of dependence all the way to singularity, and that this domain of dependence under the certain conditions never sees the global topology of our space. And so it's completely independent. So our result holds whether this space here is a torus or any kind of other manifold that you can somehow imagine that might be relevant in cosmology. I mean, there's some drawbacks with using the scalar field as a time coordinate. Reducing this kind of Lagrangian coordinate reduces the regularity of the solutions a little bit. So one has to work a little bit harder to get a consistent system of equation. But I think the result made this effort useful. So this is what I think in some sense the main difference of our result in comparison to the earlier result, and in addition to the fact that it's also much shorter. So here now comes the precise version of our result, and all of these results, whether you look at Riemann and Speck's paper or at our paper, all of these results are really mouthfuls. So they fill quite a large amount of space, and here I had to split this theorem up onto 3 slides, but obviously I don't expect that you would remember the details here, but I just want to point out a few things here, maybe because I'm really running a little bit of a time. Let me be a little bit quick here. So the first thing I just want to emphasize here is that we have, of course, an assumption on the minimal regularity that we require for our initial data. So our initial data that are supposed to be close to Fridman Robertson Walker data, and this regularity is determined by the dimension of our cosmological model, where n is here the space-time dimension. So say this is 4 for our real universe here. And just to those experts in PDEs among you, I just want to say that we have not made any effort of making this regularity here as low as possible. The point was only for us to assume a base regularity that allows us to use all the standard calculus inequalities for Sobolev spaces, like the Sobolev embeddings and product inequalities and the Moser inequality and some certain interpolation that we needed to use here. Okay, so that's just, so this is definitely not any effort to make this result as general from the regularity point of view as possible. The second thing that I want to point out is this condition, which is now our precise version of this closeness condition for the initial data. So closeness of our initial data with respect to the Fridman Robertson Walker data, which is sitting here, a 0 here and a 1 here, is measured with respect to the Sobolev HK+1 norm. So this is, for those of you who don't know what that is, this is just a norm that controls k+2 derivatives with respect to space. And that norm, where k is that number that we pick here freely up to this constraint. And this norm has to be smaller than some delta that will be implicitly constructed in the proof of the theorem. So if this smallness condition is satisfied together with some sort of technical assumptions, the main first statement is then that our result of our result is that we get existence of the solutions, and the existence is globally in time, and that's the important thing. It goes all the way from the initial time, from this t0 here, globally all the way down to the singular time t equals 0. Okay, so we really get this kind of global existence problem, or solve this global existence problem here, and we get the kind of regularity that we would expect here. The next thing that I just quickly want to point out is that we also get this kind of decay condition here, which are partly convergence, partly decay, and partly sort of possibly not optimal blow-up conditions. But what these kind of decay estimates here tell us is they give us a precise notion of this of an analog of this orbital stability that we have before, so that the solution stays close to Fridman Robertson Walker as we go all the way to the singularity. And then lastly here, this is now a precise estimate that tells us that t equals 0 is really a synchronized singularity. So R is here a particular curvature invariant. We show that this blows up at t equals 0 uniformly in space with a particular power of t that we can construct here. Right. And I think, I don't know, I probably don't say anything about the proof here. I have a few notes here, but maybe I'm going to skip over this. I just want to point out that our result is based on a method that I've constructed together with my collaborator, so with Todd Olenek and his PhD student, which was published in 2020, which allows one to prove these kind of global in time small data problems, or how to solve them for quite a large class of equations that's called Fuchsian equations. And in particular, in some sense, the main part of the proof of this theorem that I've just shown you is to show that the Einstein scalar field system can be brought to, or can be written as one of these, as an equation like that, so that we can then apply this system of equation. But there are also other things that we needed to do. So let me just really finish off here and say that that this method that we have constructed we have also shown that it has other applications, not only the Einstein scalar field system, but the Einstein scalar field system was sort of our model problem that we wanted to, by which we want to sort of convince people that the method that we had constructed is useful. I want to show that it applies to something as complicated as the Einstein scalar field system. But we've also looked at other problems, for example, which are also partly relevant to cosmology, like, for example, the Euler equations, which is also a quasi-linear system of equations on these singular kind of Big Bang backgrounds. And we found something that is a quite interesting new instability there that might challenge the standard cosmological model. Maybe I don't have time to talk about this now, but we expect that the method that we have constructed here has lots of applications, in particular in cosmology. I mean, also other applications. So this would be applications in cosmology with different kind of matter fields under different conditions. And here I've only talked about the dynamics towards the past, so towards the Big Bang singularity. But there's also very many interesting questions in the expanding direction of the universe, some of which are actually harder than in the contracting directions. But one of the interesting features that we were able to extract is that, for example, fluids that are defined on an expanding space-time, under the right conditions on the equations of state, do not form shocks in an expanding space-time. While if you define fluids, say on the normal flat Minkowski spacetimes, they generically form shocks. That's one of the important, very well-known features of perfect fluids. But if the space-time is expanding sufficiently fast, then these shocks don't form. And so we again prove a global existence result, this time towards the future, which shows that these shocks are not forming. Okay, I think I've talked enough, so I guess I just stop here. And yeah, thank you for listening.
Fantastic, Florian. Thank you very much. And I know you're all going to join me in at least virtually clapping for him. And with that, I'd like to open the floor to anybody who has a question for our speaker. If you can raise your hand if you have one.
Florian,
Yes.
You puzzled me a bit when you said it was more interesting to mathematicians than physicists.
No, I mean,
what?
So I think.
Sorry, just finish. So presumably we're looking, has some relevance to the period in the early universe.
Yeah, I mean, the problem, of course,
but it's still in a fairly uniform phase.
The problem, of course, in the early universe, the very, very early universe. So we're talking about the asymptotics, right, at t equals 0 here. So the leading order dynamics. What physicists expect is that there will be some sort of quantum phenomena in that space-time. And I'm just dealing here with the classical theory of general relativity. But nobody, I mean, it depends who you ask. But to my understanding, there is not a full theory of quantum gravity or anything. So nobody really knows what the equations are, the real equations are close to the singularity. So for me, it is more like an effort of driving the classical Einstein's theory to its limits, right? And see what happens, which is then, I think, useful information also to physicists, because that might tell them how to quantize the classical theory when they really understand the sort of limits of the classical theory. So I think in that sense, it's definitely interesting for physicists, but it might not be interesting sort of from the observational point of view. And that's what I meant.
Thank you.
Any other questions? Chris?
Hi, Chris.
Hi, Florian. How are you?
Good. How are you?
Good. I just wanted to ask about the scalar field that you drew to constrain the instability around FRLW.
Yep.
Is that sort of a specific choice, or how was that chosen, and is there any meaning to that?
Yeah, so I mean, that's a very specific choice of a scalar field that people have considered so far in this for this purpose of quiescence, right? So this is a scalar field that is, I mean, minimally coupled to the Einstein's equations, and you choose a zero potential. So this is so just a free scalar field. So the scalar field itself just satisfies the linear wave equation, and it's coupled to the Einstein's equation. One of the interesting questions then is, of course, what kind of potentials can you introduce, non-zero potentials that you can introduce in order to get, let's say, the same dynamics. My former PhD student, Josh Ritchie, has looked at this numerically in his PhD thesis and found some conditions on the potential that allows us still to see the same dynamics as for the free scalar field. But it is just one particular constructed scalar field that seems to, or kind of a meta model that seems to solve that issue here, maybe to get rid of these horrible Mixmaster dynamics.
So can you interpret that as a particular meta model that means something from a physical point of view? That's a hard question.
Yeah, no, that is, I mean, I think according to what Josh found in his PhD, with the you can, for example, you would get the same result here with a potential that people usually use for the inflaton. So for the that is the kind of meta model that is supposed to drive that rapid expansion in the early universe. But I have not. That's one of the next thing I want to do, is to understand our result here with the potential and see what kind of things you can draw. But I mean, what the inflaton really means physically, I don't really know. So I think you can ask the same question about that one.
Cool. Thank you.
Anybody else? If not, I guess I do have a question. Now, as you know, I don't really understand much of general relativity and all the systems of equations, but I do understand something a little bit about convergence. And you basically said, with respect to one metric, there's Mixmaster chaos going on. And so you came up with a different metric, and now you're taking t to 0, and still things remain bounded. Is that about right?
No, the things are not bounded. So we get a curvature blow up, right?
But
So
the distance between you stay close if you go towards t equal to 0, right? And your new metric.
Close to the solution that blows up,
Yes.
right? That has
Yes,
a singularity.
exactly.
So we get a uniform blow up.
Yes.
Well, for Mixmaster dynamics, we would get blow up, but with addition, all these basically chaotic kind of bounces going on at the same time. And
but I guess my question is, I think I understood that you now have a metric where the blow up basically is the same, it happens at the same spot or something, so that you remain close.
Yeah.
Now, is it the case that if you use that metric and start at time close to 0, that is close with respect to that metric, do you remain close going back to current time?
Yep.
Because I mean, it's quite easy to come up with something that, well, this is go to 0, because after all, we have all kinds of, a free choice of what metric you want to choose. Is it at least something that is then consistent, that if you stay close, start close, that you remain close?
Yep. So this is then the sort of complementary problem. So here we start from some finite time, say the present time, go backwards in time, it has stability, and then the complementary problem would be start from the singularity and go the other way, and also prove a stability result for that. We have not done this for this particular problem yet. We have done this for the perfect fluids, for example, and in that case, you can really get a stability both ways. Okay, and but here we haven't done that for the Einstein scalar field system. So that's one of the next things that we want to look at. But I expect this to be very difficult, because in order to go back the other way, you really need to have a very good, I think you will need more precise asymptotics than we have at the moment. I mean, at the moment, we have certain decay estimates, so saying that certain quantities go to 0 or certain quantities converge to other quantities with a particular rate and time. But in order to go the other way, we would probably need to know a little bit more what it really converges to, and so on. So this is just my experience from the Euler equations, is that you need understand more of the asymptotics if you want to go the other way. And at the moment, I don't understand that much of the asymptotics for the Einstein scalar field system to be able to do it, but we're working on that.
Excellent. Thanks. Any other questions? If not, then I guess let's thank our speaker again, and we'll reconvene at least at next seminar series. And I have no idea when that is, but it will be surely published on our webpage.
Thank you for listening, everyone.